Um, so today I'm going to talk about a couple of things that we've been doing in the lab and the recent things that we've been working on in relation to brain geometry and how it relates to a couple of the things that we see in the brain, including dynamics, function, and even the way areas are formed in the brain. So I'd always like to start with this one because we're in a physics environment. I'm sure you've heard of this phrase before, function follows form. But obviously the definition of function and form in here are very loose. But in principle, this kind of relationship is true in any kind of almost every physical system, right? Just to pay homage to the recent British Grand Prix, we know, for example, in aerodynamics, it's really, really important that they create the perfect structure to make the F1 cars to be as aerodynamic as possible. So again, I'm losing the terminology form in here, right? But it's also present in various other systems, typical acoustic systems. It's really important that you understand the tension of the string because that relates to what kinds of notes will emerge from that particular instrument. It's also present, say, in hydrodynamics, right? So if you say you have a pond, then you have different structures in there. You will know eventually that different types of wave physics will emerge, basically just because of certain blockage or certain flow that will propagate in that particular system. And it's also true in a lot of biological and chemical systems. For example, here it's just the protein structure, right? That certain structures of the protein will be amenable to certain function, and they will be they have a strong affinity to other types of proteins with almost similar structure. So this kind of relationship is very ubiquitous in physical systems. So we know that the brain is inherently a physical system. It's embedded in three-dimensional space, and it has a three-dimensional structure. So that's the reason why in this talk, I'm going to kind of follow through that same kind of line of thinking and ask questions on if we just look at plainly the geometry of the brain, can we actually say something about its emerging dynamics and function? And also, again, as I mentioned, the way areas are organized in the brain. So I'm going to focus on these two things that we've been working on in the lab. So I'll start with the top one, dynamics and function. If you look at data, for example, imaging data that measures neural activity in both space and time. And I'm going to focus here, for example, on a macro scale level, fMRI. So this is a typical functional MRI activity. I didn't do anything on it. I didn't do any kind of smoothing. It's literally just the raw data. I've just projected the three-dimensional volume of fMRI to what we call as the surface, basically on the surface of the brain. And you can see that you can identify, if you keep looking at the video, that activity propagates mostly smoothly, right, in space and time. It's not jumping from one place to the other. Obviously, this is resting state. A different scenario might happen if you have perturbations or kind of task-related activity. This is resting state, assuming that your brain is just constantly trying to survive in a way. You can see that the activity propagates smoothly in space and time. And this is typical of, say works by Leo that shows that the brain intrinsically have this wave-like activity. This is true not just in humans and not just in fMRI. It's also true in other types of modalities. So here, for example, I'm showing you a typical optical imaging for a mouse brain. And you can clearly see that there are waves that emerge spontaneously and they propagate in space and time, but they also transition between one pattern to the other. And people have also found it in task-related fMRI. So these kinds of things are ubiquitous in the brain. So the first thing as a physicist is how do we model such kind of things? So I would lean a lot on neural field theory. If you heard of it, but I'm going to explain a little bit of it in the next couple of slides. But I'm just going to want to highlight that neural field theory has been really successful in the computational neuroscience world and has predicted a lot of features of brain data. I'm going to show here an example of neural field theory, which I would call Robinson et al. So Robinson was my PhD supervisor. And he's pioneered a lot of neural field theory that encodes space and time simultaneously. Again, this is kind of a little bit different from neural mass models, if you've heard of it, or brain network models, where you have discrete nodes that are connected by, say, a white matter connectivity. In here, you kind of measure the excitatory and inhibitory activity continuously in space and time in the cortical medium. A particular example here is the Robinson et al. Corticothalamic neural field theory, where you can have 4 different populations, 2 in the cortex and 2 in the thalamus. And this simple kind of model has predicted a lot of features, say, in EEG. It fits a lot of the power spectrum of typical EEG data, especially the harmonics. It has predicted seizures. It has predicted, it can also be used to do state tracking. So basically different sleep states, for example, and even anesthesia. And I'm gonna lean a lot on the kind of the latest kind of development in the neural field theory, where it now focuses a lot, because most of these things are, so you solve neural field theory in space and time, but you also take an average to kind of compare your simulations to, say, in EEG, just your discrete electrodes, right? So you still do some kind of spatial average. But you can extend neural field theory to predict certain structures in space and time without spatial averaging. And it can describe the physics behind why we get standing, traveling, and different types of rotating waves as well. So again, I'm going to lean a lot on this neural field theory concept. So one biggest assumption of neural field theory is it doesn't need your typical white matter connectivity of the human brain. So obviously we know that the human brain network is highly complex, right? So it's kind of difficult to model that kind of phenomena. Physicists love doing approximations, right? So one simple approximation of neural field theory is approximating its connectivity kernel, so its connectivity profile. And it focuses a lot on very local and very EDR. EDR means an exponentially distance rule connectivity. I'll start with local. I'm showing you here a slice in a cortical column, for example, and I'm gonna try and ask you to look in these kind of regions, right? We know, so say this is one cortical column and we have another, they are intrinsically connected by long-range connections via the white matter. But we tend to forget that if we just look at the cortical column itself, there's actually a lot of these very local lateralized connections, the very nearest neighbor connections. And that's true even when you do high resolution electron microscopy in different animals. So see, all these neurons are tightly packed in a small volume of the cortex. So intrinsically, you have a lot of lateral and local connections in here. So that should kind of have an effect in your overall dynamics. The next is the exponential distance rule. You see, I'm showing you here a typical diffusion MRI. So here we're plotting the weight that you get as a function of fiber length. So basically just a weight versus distance metric in logarithmic, semi-logarithmic scale. So you clearly see here that the typical profile is exponential, but you also have exceptions. So basically the red dots. So you have long range exceptions, but most of the connections actually follow this really simple exponential function. And again, this is true not just in humans, it's true in other species. So say a marmoset. And it's true not just in diffusion MRI. So for example, in this marmoset, this is obtained via track tracing. So you inject a viral tracer and then you follow the track to get to the location. So the assumption is track tracing is a more accurate kind of representation of connectivity than diffusion MRI. But they see the same effect. You have this exponentially, this decaying rule. And again, it's true in mouse, macaques, and so on and so forth. So this is a very nice assumption to lean on because it's true. We see it a lot in data. So again, neurofield theory approximates a lot of the biophysics behind spiking, fire rate, and relationship between populations. I don't think I have the time to fully explain neurofield theory, but I'm gonna quickly walk you through a typical neurofield theory. So neurofield theory, say you have some activity field. So again, it's a spatial temporal field. So this is the field from population B to population A. That could be from excitatory to inhibitory or excitatory to excitatory, or it could be a thalamic population to a cortical population, whatever flavor you want. Neurofield theory will approximate some average kind of large scale effect of the dendritic filtering that happens in the single neuron level to get some to get a population postsynaptic potential. And from there, you again assume again that you have this neuron. You assume that a lot of potential come from different populations. So you assume some kind of integration, just a simple summation to get the average potential of the soma. That will lead to some changes in the firing rate of population A. And you can employ some kind of a sigmoidal function to it. And the most important thing is how do we get back to the activity field? So basically, neurofield theory assumes that the activity field is actually a result of the firing rate of population A. And it's governed by this equation, which I will describe in the next slide. So basically, you have this kind of loop that changes activity field to potential to firing rate and back. And this happens in multiple populations. So again, I'm going to focus on this kind of term in here. So this is just a simple damped wave equation. And it's a very simple kind of physics-like damped wave equation. Again, it solves the activity field phi of population C due to the firing rate of population A. And this is the firing rate of that population. And this is just some of parameters. For example, this is the damping rate and some length scale. I'm going to focus a lot on this. So this is the Laplacian in Euclidean space, or Laplace Beltrami operator in a more generalized manifold. But that encodes a lot of the spatial information in your system. And if you do assume that phi and q, for example, are separable in space and time, you can simplify this equation, and you will get that to solve the spatial component of your solution, you will end up with the typical Helmholtz equation. So it's a very typical separation of variables. So again, this Helmholtz equation will now provide you, if you solve this, it's just like an eigenvalue problem, right? This is the Laplace Beltrami operator. Again, this is the one that defines the geometry of your system, in this case, the cortex. And if you do this eigen decomposition, you'll get the family of eigenvalues and the eigenmodes, which I will talk a lot in the next couple of slides. So what do I mean by the geometry of the cortex? So this is a typical T1 weighted structural MRI. You can employ a lot of automated segmentations, and you will get an approximation of the boundary of basically what we call as the gray matter surface, basically just the top layer in here, this curvature in here, and this is the result that you'll get. So this one already encodes a lot of the gyri, the salci, and so on and so forth. So if you kind of plug this surface in the definition of your Laplace-Beltrami operator, you will get the set of eigenmodes. Again, this is very typical of, say, the eigenmodes of a one-dimensional string. It's very similar profile. You have the first mode as some kind of a uniform kind of spatial profile, and the next three would be the one with single nodal line. So again, very similar to spherical harmonics in quantum mechanics, and again in one-dimensional strings. But this is again the cortical geometry of the surface. You can also solve this equation if you have a volume. So here I'm showing you again, this is T1 weighted MRI, and I would mask, for example, the thalamus in the subcortex. And this is the kind of the three-dimensional structure of that thalamus. You can use that again to define your Laplace-Beltrami operator. Obviously it's a bit tricky now because in this surface, it's easy because you can have in physics, for example, how to represent the surface of this one, it's easy to just represent it as a mesh, right? You have a point that are connected with this nearest neighbor. So that's actually what you're seeing in here. Obviously, a three-dimensional volume is a bit tricky, right? There's no inherent, the neighborhood is now three-dimensional. So you can actually do a tetrahedral kind of mesh. So instead of a one point with almost approximately 6 neighborhoods, in this case, you have, I don't know how many, 1, 2, 3, 4, 5, 6, 7, 8. You can imagine it. So a tetrahedron. And then you now plug that in your definition of your LBL. And again, you will get the set of eigenmodes for that particular structure. And again, you can do this for any kind of structure of interest. All right. Sorry, yeah.
Has it been done for the hippocampus, for instance?
Yep. I'll show you later that we've done in the hippocampus. You can do it in the cerebellum if you want, in other amygdala, and so on and so forth.
Just one question.
Yeah.
You talk in the question of this, the result is dominated by the boundary condition.
Right.
Now, so that means that you neglect completely the structure inside the brain.
Yeah.
Just take the boundaries.
Absolutely. Yeah.
So you assume that
everything else is. Yeah, exactly. Yeah. Yeah, that's why most of the things that I'm going to show here is the structures are independent in a way. We don't have interrelationships between the neighboring structure, for example. Yeah. Exactly. Yeah.
So then, I guess that then you have to solve a different equation, including a field coefficient in front of the population.
Yeah.
In which you have some density of connections per point.
Yeah. Actually, I'm going to show in a couple of slides how we can modify the Laplacian to incorporate these things. And again, typical physics sets of modes. You can use this as a basis set because they're independent, right? They're orthogonal to each other. And you can do the same thing with brane maps. So again, you have a particular brane map of interest, whatever that is, in fMRI, for example, and you can now represent that as a linear combination of your modes. Very typical physics. And again, you can do that in just spatial maps, but you can also do that in spatial temporal maps. So what we do in here, for example, is we have a time snapshot, and then we calculate the coefficients in one time point, and we repeat that process in multiple time points. So you now have a spatial temporal coefficient A. All right. So when we did this, I'm going to start with the story. I'm showing you here a typical task fMRI map, and these are group averaged, so that's why it looks a little bit smooth. what do I mean by that? So basically, if this is from the Human Connectome project, if you've heard of it. So basically, you ask a particular participant whilst inside the scanner to perform specific tasks, say related to typical motor behavior, working memory, typical linguistic tasks. And what people do in fMRI is to find which parts of the brain are activated when the person is doing that particular task. And these are your prototypical maps that you will get when a person is doing the task. And again, if you do your exercise of using the modes to reconstruct your data, you can see that about 100, most of the information is already encoded in your first 100 modes. And if you do the same exercise and sweep through the number of modes, you can see that, yeah, if you keep increasing it, you'll recover the full data, which means the geometric modes are a really good basis set for this, for any kind of activity within that happens on top of that codiform manifold. But when we did this, we were also thinking a lot on white matter connectivity, right? We can also construct basis sets from white matter connectivity. And that's exactly what we did. So folks, we created multiple types of connectivity, say a artificial synthetic exponential distance rule connectivity. Or we can also create the connectivities directly from the connectome, basically the full white matter connectivity. So basically what we wanted to ask is the geometric modes really a good kind of basis set relative to other types of anatomically derived basis sets? And what we find is yes. And this is, and we were happy. We were happy, and we stopped there. But a lot of people obviously inferred a lot of different things from this plot, saying that connectivity is not important. But again, we were not saying that. We're saying that in a continuous macro scale kind of activities, say fMRI, the geometric modes seem to be the more parsimonious basis set than other basis sets. It's not saying that connectome, for example, is not important. So we had a lot of trouble kind of relaying this kind of information to a lot of people. But we also were asking, actually, is this really true? This poor performance of the connectome type of basis set? Is it just a result of, I don't know, diffusion MRI? Because inherently diffusion MRI is very noisy. You have a lot of approximation to follow the white matter trajectory. So we were asking, can we find a connectome that is as accurate as possible and not diffusion MRI based? Obviously, we can't find that in humans. So we lean on some animal studies. So there's this study in Science Advances in 2020 that has reconstructed a voxel resolution mouse connectome based on track tracing. So basically, it's a Allen Institute data, and they've reconstructed the full connectome in the entire mouse brain, and it's based on the track tracing. So to us, this is probably the best connectome that you can find for a species, right? So we did that. We used this data and performed the same kind of methodology as what we've done in the previous slide. So say here, I'm showing you a typical map, a gene expression map, a sodium-related gene expression map. We can calculate the modes of the mouse brain in here. And we can also calculate the modes of that track tracing connectome down the bottom. And we can perform the same exercise of reconstructing the data. And again, you see that geometric modes seem to be working better as a basis set, even in the mouse brain. And that's true in a lot of the maps that we see, gene expression, fMRI, calcium imaging, and so on and so forth. So our student is trying to finish this paper soon. So hopefully it will come out in the next couple of weeks. So to us, it is kind of a little bit of a relief saying that the result that we got previously is not an artifact. It's not a diffusion MRI artifact, but there is something fundamental in it. Right. Now, going to Leo's question, we can perform again the same exercise in the subcortex. But one of our collaborators were doing a lot of gradients in the brain. I'm not sure if you've heard of gradients. So basically, you take a connectivity, functional connectivity, for example, and you apply some low dimensional approximation to it. You can do a typical PCA, or people do some diffusion map embedding, which is the nonlinear case, basically trying to find a low dimensional representation of that connectivity. And by doing that, you will get what we call as functional gradients. So we were going to do a reconstruction of the data in the subcortex, but when we first saw this one, we thought, oh, hang on, there is actually I don't know, they seem to be aligned. I don't need to do any reconstruction. The modes itself are actually producing the low dimensional representation of functional connectivity. When I got this result, I thought I was making an error. I thought this is not true. But it's true for not just the first one. You can go to the next kind of gradient. So basically, the gradients are arranged in terms of the amount of variance that they explain in your data. And we see the same effect. The modes and the gradients seem to be almost perfectly aligned. This is the thalamus. We did the same in the striatum in here. And we also did the same in the hippocampus. And again, the alignment is almost perfect, suggesting really that maybe in the subcortex, this very local EDR connectivity again. But take note, these gradients are based on intrathalamic functional connectivity. It's not looking at the connectivity outside of the thalamus. So maybe it is not surprising that in this little small structure, very local EDR connectivity really dominates, and that the geometry can provide you the information directly of your function. Right. Now we do my favorite bit, which is actually using the modes to model activity and dynamics. So let's go back to the near field theory equation. What I wanted to do is strip away all the intricacies of the near field theory and basically ask a really simple question. How far can we go with just cortical geometry and a description of wave dynamics without your intricate, firing array and so on and so forth? So I will go back to this equation. And again, it's really simple because you only have one parameter in here and another parameter in there, and I can fix one of them to make it as simple as possible. So basically, I can solve the activity in the cortex. And what kind of Q shall I use? I mean, a lot of modeling works would assume that if you want to model a resting state, you can just use a Gaussian noise, right? So that's what we did in here. So we replace Q with a Gaussian noise and solve phi. What do we get? So you'll get a typical activity like this. Again, it's not surprising because again, you use the wave equation to get waves of activity. But the question is it actually a good model of fMRI, resting state fMRI? So I'm showing you here the group average FC in the Human Connectome project. And this is the model that we get. And we also compare that with your typical neural mass models, where it's a model again of discrete nodes that are connected by white matter connectivity based on diffusion MRI. And most often than not, they have more parameters intrinsically. So in here, we use that model and we tune 4 of the parameters. And we kind of compare these two models side by side. And I'm not going to explain the details, but you can use a lot of the different metrics in this field that we have, say, looking at how correlated each kind of point in this matrix with the empirical and the model data. So that's all the points that you're seeing in here. You can do some node average. So basically you take an average of a row or a column, and then you compare the data and the model. Or you can do some time, like temporal dynamics. So at every single time point, you kind of measure the synchrony and so on and so forth. And that's what I'm showing in here. But ultimately, what we found is it seems like the simple wave model performs equally or even better than the more complex neural mass model. That means really that if you have a simple wave model on the geometry, you can go really, really far with it. And to us, we always like models that are simple, but are predictable of multiple things, right? You can also model evoked activity. So in here, for example, we ping the visual cortex and just allow it to freely propagate without any other external stimulus. So it's a step function stimulus. And then what do we get out of this? What we did next was to follow the activity along what we call as the visual hierarchy. So this is a typical map by Van Essen and Feldman, where they showed that if you follow the input from the retina to the LGN to the visual cortex V1, V2, V3, it will follow this hierarchical kind of organization. Basically, yeah, the activity kind of gets passed on to the next hierarchy and so on and so forth until you get to the higher order cognition. So what we did was to find regions in the human brain that kind of mimic this hierarchy, because this map was created based on a primate brain. So that's what we did in here. We get the regions in the brain that follow this hierarchy in here. And we just measured a simple time to peak, basically how fast the signal will propagate in that particular region of the brain. And what we found is, I'm comparing here time to peak, basically the peak of this activity in there, and comparing it with what we call as intracortical myelin. Basically, if you have T1 weighted MRI and T2 weighted MRI, just take the ratio, it will approximate the myelin content in the brain. And this is myelin content is probably very, I don't know, very popular in the field because it's an approximation of, again, the hierarchy. Basically, regions in the sensory area, visual cortex and the motor cortex in here will have the highest myelination, and the association areas will have a lower myelin content. And what we find is that the time to peak and this approximation of the hierarchy seem to match very, very well. And again, it's just a wave that propagates in space, nothing else. And you can kind of go far, really, really far with it. Okay. Now we go back to the question a while ago on the brain is not intrinsically uniform, right? There's some heterogeneity in it. So again, the neural field theory wave model assumes that the cortex is homogeneous. That means every single point in here has the same property and that the activity propagates isotropically and homogeneously in space, right? But we know that the brain is not isotropic, it's not homogeneous. You have variations in, again, intracortical myelin, variations in cortical thickness, or even some kind of synaptic density, variations in genetic profile. You can list as many kind of variations as you can imagine. How do we model these kinds of effects? How can we incorporate that in our models? So you could imagine, right, that if you have a homogeneous case, if you ping the brain in one region, naturally it will just dissipate in space and time, and it would traverse the system in all directions uniformly. But if you have some kind of heterogeneity, some kind of a boundary condition, if you may say that, you will now change the profile of that propagation. It took us a while to kind of model this effect because it's not obviously commonly done in the neuroscience world. But we found this paper, I think it was written by a physicist, and it's been on the archive for, I don't know, 20 years or something. Basically, what we can do is, all right, this is my homogeneous wave equation. You can change the definition of your Laplacian by just inserting some kind of a tensor inside D. And you can define that tensor in whatsoever way, but it's a tensor that will now encode changes in your direction according to some changes in your curvature. And how do we define this D? Again, you can define it in various ways, but what we found is that we can, the simplest definition that we can do is that approximate it as a identity matrix following some kind of a sigmoidal function. So here, rho is the heterogeneity that we encode in your space. It could be whatever map that you have. And alpha is some kind of a tuning parameter. And so by doing that is, if my alpha is 0, I will go back to my homogeneous case, and I can test alpha in both kind of negative. If my alpha is negative, I will go in the other direction when it's positive. So we now try to redo all our modeling using this heterogeneous case. And we use various types of heterogeneity. Again, we have synaptic density. We also have approximations of genetic expression in gene profiles that are highly expressed in the layer 4. And again, the reason why we do that is layer 4 is has a lot of innervations to the thalamus. So that's where the cortical thalamic kind of loop kind of innervates. So we feel like that could have a lot of impact in your overall cortical dynamics. Cortical thickness, obviously. We also have maps of ratios of excitatory and inhibitory activity. And again, my T1, T2 intracortical myelin. And then again, we use typical measures of FMI in the FMI world, to approximate the statistical properties of your empirical FC in this case. This is the homogeneous, and say this is the T1, T2. And you can see that you can kind of squint and see that if by incorporating T1, T2, I could kind of replicate kind of more accurately some properties of the empirical data. And again, you can do that exercise with all the others. So the question is, quantitatively, is it actually a better predictor? And again, we actually changed the values of the alpha parameters when we did this. We optimized it to the empirical data. So you can, again, look at all the different metrics. And I'm summing all the metrics just for simplicity. And we've arranged this in increasing order, basically which one's doing best. So I'm going to make you look at just the last plot in here. Again, this is the fit. And so this is the measure, the metric. And these are the different maps that we have. And you can see that the T1, T2 seems to be the one that has increased the predictive power of our wave model. But to be honest, it's not a lot, right? It's just about, I don't know, 30%. So there is still room for improvement, I suppose, because we've assumed still that the waves propagate isotropically. But we know that there could be some changes in the X, Y, and Z direction. So you can incorporate that complexity later on. But we were still kind of happy with it, that we will have some kind of a working model that incorporates some kind of heterogeneity. So we asked, is this applicable to other types of species? Always want our model to be as generalizable as possible without any tweaking. So we have a lot of data in the lab on marmosets and macaques. So here I'm showing you a wave model using the marmoset cortical geometry and macaque wave model, again, using its cortical geometry. And again, the wave model itself is the homogeneous case, is predicting the empirical data reasonable, right? If you are in this modeling world, once you get a correlation of about 0.4, I think you are happy. It's very rare that you will get modeling works in my field that will get you to, like, say, 0.8 or so. But so for us, a 0.4 to a 0.6 seems to be reasonable. Again, for a really simple wave model. And again, what we found is by incorporating the heterogeneity, you improve the predictability of the models, and they have differential effects, different maps. For example, in the marmosets, we have data on, actually, I'm going to focus here. We have data on cortical thickness, approximations of the density of cells in those marmosets. In the macaques, we have also data on receptors. So basically, various levels of density of different types of receptors in the macaque. You can see that they have differential effects, but the T1, T2 seem to persist, except for the macaque. So to us, again, that is a success of the model because he has predicted in a more generalized way various dynamics and in various species. So I think I've spent a lot of time, but I think I can stop here if because we only have like an hour, right? Yeah, I can stop here and we can have a discussion instead. So basically, just to summarize what I've shown in here is that the geometric eigenvalues seem to have a lot of good value in here because it can account for a lot of the constraints in function across different species. It is tightly linked to some theory, which is near field theory. It's more than just a basis set because, again, it can predict dynamics. But it emphasizes that really simple connectivity could provide you a lens in fMRI data, and that the effects that we see are consistent not just in the cortex, but also in non-neocortical structures, and that traveling waves seems to be sufficient to explain a lot of the various phenomena that we see. So I repeated myself. I can stop here now. Yeah.
Thank you, James. It was a fantastic talk. You guys have questions?
Thank you, James. Very interesting. You explained us how to obtain waves propagating the resting state. How would you incorporate now sensory input to your model to predict something else?
Good point. I think you can try and, because we're toying, I mean, we asked the same question in the lab, and how do we best do that? One thing that we can do is, where's the wave equation? You can change a lot. You can change this equation. You can change the right-hand side of the equation and add whatever flavor that you have, right? You can have colored noise. You can have a cue that has an input to different regions simultaneously to kind of mimic sensory evoked. Kind of similar to what we did in the visual cortex, but maybe a more structured kind of input, because in that case, we only did like a step function. Maybe you can have something more sophisticated, but you can add whatever flavor that you have in here. The tricky thing is obviously solving this equation in the cortex. That's tricky. Most of the things that we have done is to make sure that our cue in here is kind of linear. There's no non-linearity. So I can solve this equation much, much simply using some separation of variables. Other than that, we need to calculate the Laplacian numerically more accurately, which is the tricky thing to do.
Would that indicate that if you have, for instance, an auditory signal or visual signal or tactile signal would represent different R values in your?
Yeah, that could do. I mean, again, this is the basic of the basics. You can change a particular length scale, for example, in a different region of the brain. You can have some kind of head. You can also edit this. You can have some kind of reverberation. You have like a feedback if you want to. You can change the cue to also have inputs from the subcortical regions, but in a much more simpler way. So say you have like a time delay, kind of imagine that you have an input, it goes to the thalamus, but it just goes back in a time delay fashion without doing any kind of nonlinear effect on it. You can easily do that in the cue. So if you want to do something on it, I'll be happy to chat, because we've been thinking a lot on how we can incorporate these kinds of different modeling.
Yeah, one question. So near field theory was first developed, or at least found very strong applications on EEG data. And then you apply it to fMRI, which is this bald signal that's much slower dynamics. Have you tried to do a similar approach with more complex dynamics with EEG or MEG data?
No, actually. MEG would be nice, actually, because I think there at least you have smooth. Because the tricky thing with EEG, right, because it's discrete. So I need to have some kind of approximation of averaging. Obviously, there are high density EEGs now, so it's not as discrete as it was before, but still you have some kind of, you lose some kind of information. MEG could be a nice thing, because you can do some source localization.
The model, the wave equation model is linear. So basically, as far as this reproduces what the brain does, it just says that the brain just linearly processes the information it receives. Typically, when one is close to a steady state or to a rest state or whatever perturbation, the system reacts linearly and gets damp. And of course, the most that are excited are the less damp, and those reflect the behavior. So this might be suitable to reproduce, say, what you observe close to rest state or whatever. But when you push the input beyond a certain limit, typically you excite non-linearities of the system. So do you think that this equation is suitable to model, say, big responses to a strong, say, a strong stimulus, or would you think that you need to include some nonlinear terms in phi in the field or whatever?
I think with its current form, I don't think it's amenable to a lot of these strong activity inputs to cause nonlinearity. But neurofield theory has a version now that allows nonlinearities to happen. So, but again, you need to add like a couple of other equations in here to kind of make sure that you don't push the system to a kind of breaking point.
You need either a saturation term cubic, or you need an extra equation.
Yeah.
May I ask a question myself?
Where does this sound? Ingo?
Yeah.
Oh.
May I?
Yeah.
Oh, first of all, great talk. Thanks a lot. You emphasize also on this slide that geometry is important, and you compared different species with different geometries of the cortex that you modeled. What differences did you find for the different geometries? So what influence do you find in geometry, for example, in terms of eigenvalue distributions or similar properties?
To be honest, sorry. To be honest, the species one is a very recent results that we got. This is really like off the press, couple of weeks ago.
Mhm.
And again, our student is trying to finish it. What we found, for example, is the length scale is completely different, which is
Alright.
expected, right? Because the brain of marmosets are much smaller, right? And
Mhm.
marmosets are lissencephalic. Actually, this is wrong. This is the marmoset, and that's the macaque. Sorry, because this image should be on top, and this one is below. Because marmosets are lissencephalic. Basically, their brains are very smooth.
Mhm.
They don't have a lot of gyrification.
Mhm.
So to us, actually, we
So
were.
what is the consequence of that? Do you, for example, do you have any eigenvalue distributions that one could see
Basically,
differences?
the waves propagate much faster. So that's why because the waves are kind of inherently the speed of the propagation is related to how damped your wave is and the length scale, right? They
Mhm.
just
Mhm.
we found that means the length scale of the marmosets are much kind of smaller.
And that would be rather the influence of size, right? But what
Yeah, correct.
what
Yeah.
about the influence of the shape?
The shape itself, good
Mhm.
question. We haven't really looked into it that much.
Mhm.
But yeah, we've never really looked into, say, for example, here in the macaque, the sensory areas seem to have this big innovation, a big kind of valley in here compared to the
Mhm.
marmoset.
Mhm.
We've never really looked into it thus far.
Thanks a lot. I'd like to discuss that a bit further
Yep.
with you later, maybe.
Yep. Again, if you're interested in doing species kind of work, we have a lot of data on marmosets, macaque, mice, even other kinds of primates such as chimpanzee,
Mhm.
colobus,
Mhm.
whatever you can think of. We have it.
Great. Thanks a lot.
We don't have any other questions? So let's thank James again